Welcome to the lecture on Navier-Stokes equations for Newtonian fluids. So, we had discussed about the conservation equations, we discussed about the equation for the momentum, continuity, and also about the energy. So, especially if you look at the momentum conservation equation or the energy equation, we had the x momentum or y momentum or z momentum equations, then you had the energy equation. In all these equations, what you see that you come across the viscous stresses term. So, the governing equations of momentum and energy, they contain unknown viscous stresses terms, that is tau xx, tau xy, tau xz or xy or so. So, now these need to be expressed in a measurable manner, and they are basically expressed as the function of local deformation rate or the strain rate. So, in that case the equations will have something by which you can, so you can do the experiment, you can measure those strain rates, and further you can calculate the values. So, those stresses are basically expressed in terms of these strain rates. So, mostly what we do is normally when we talk about the three dimensional flows, in that the local rate of deformation is composed of linear deformation rate as well as the volumetric deformation rate. And if you talk about the linear deformation rate of the fluid, it has 9 components, out of which 6 are independent for the isotropic fluids. So, they are normally denoted by Sij. So, that is the linear deformation terms, and their suffix ij will have similar meaning the way we try to even define for the stress terms. So, in that only we are also defining them. So, if you talk about the linear terms, so you will have the linear, so you will have linear elongating deformation components. So, they are the 3. So, those 3 are basically the Sxx, Syy and Szz. So, their values are dou u by dou x, Sxx is, then Syy is dou v by dou y, and Szz will be dou w by dou z. Now, you have apart from that, so as you had we saw that we have 9 components. So, you have 6 shearing also components, so shearing linear deformations components. So, they will be when, so in the Sij when I equal to j, so that will be linear elongating deformation component, and then you have shearing linear deformation components. So, in that you will have the S xy or Syx you can have, and they are normally defined by half of dou u by dou y plus dou v by dou x. Similarly, you have Sxz or Szx, they will be half of dou u by dou z plus dou w by dou x, and accordingly Syz or Szy, they will be half of dou v by dou z plus dou w by dou y. So, this way you have the 9 strain rate linear deformation rate components. So, then these are deformation components. Then we have the volumetric deformation, and volumetric deformation will be defined by, So, that will be dou u by dou x plus dou v by dou y plus dou w by dou z. So, that will be dou u by dou x plus dou v by dou y plus dou w by dou z. So, that way that is also can be represented by div u. So, so what is seen that these are the strain components. This will be required in our coming studies. So, if we talk about the Newtonian fluid, now in the Newtonian fluid the viscous stresses are proportional to the rates of deformation. So, as we have understood earlier also that they will be related to that rates of deformation. And in the 3-dimensional form of the Newton's law of viscosity for compressive flows, you will have two constants of proportionality comes. We talked about the Newton's law of viscosity and we saw that there the proportionality term is coming, that is coefficient of viscosity. Now, in this case when we talk about the compressible flows, in those cases we deal with two constants of proportionality, and that is mu and lambda. So, mu is known as the dynamic viscosity, which will where it will be relating the stress to the linear deformation. That is what we have seen in the case of Newton's law of viscosity earlier. But in the case of compressible flow, you have a second term, that is second viscosity lambda. So, this is used for relating the stresses to the volumetric deformation. So, this which is happening in the case of compressible flows. So, now this stress values, substitution of these stress values in the strain rate terms give rise to the Navier-Stokes equations, and how that is that we will see. So, what we have seen that since there are these two lambda as well as mu, these are the constant of proportionality is used, and if we define the viscous stress components. So, you have the 9 viscous stress component tau xx, tau xy, tau xz, tau yx, y y, yz. So, altogether you have the 9 viscous stress component which are encountered in the momentum as well as the energy equations. Now, these components of the viscous stresses, they can be expressed so they are expressed like in the term of the lambda and mu, and also the deformation components. So, what you see is tau xx, it is defined as 2 mu dou u by dou x plus lambda div u. So, that is div u. So, that is for the tau xx. Similarly, tau yy will be 2 mu dou v by dou y plus lambda div u, and tau zz will be again 2 mu dou w by dou z plus lambda div u. So, that way we have these 3 stress component, and then out of that you have out of the 9, 6 are independent. So, basically tau xy will be taken as tau yx, and this will be mu times dou u by dou y plus dou v by dou x. Similarly, tau xz equal to tau zx. So, that will be mu times dou u by dou z plus dou w by dou x, and tau x, so yz or tau zy, it will be mu times dou v by dou z plus dou w by dou y. So, that way you have these viscous stresses which are there. So, they can be expressed in terms of these deformation components, and these components. So, these components values when they, so they these are expressed in terms of strain rate, and then when they are written for the these momentum or the energy equation in terms of the strain rate terms. So, that was done by independently by two scientists, Navier as well as Stokes. So, that is why these equation which we obtain is known as the Navier-Stokes equations. So, the term that is lambda, so not much was known about lambda earlier, but its effect is said to be very small as compared to mu, and it is normally said to be about minus of 2 by 3 mu. So, lambda is said to be, that is said by that is basically suggested by Schlisting. So, Schlisting was also a researcher, and on his name there is a book also. So, he has suggested the value of lambda as minus of 2 mu by 3. Now, for the incompressible flows, so we know that dive u becomes 0. So, that way you have accordingly you can have many meanings for the incompressible fluids, and then you will have the terminologies. So, once you substitute these values into the momentum equations, x momentum, z y or z momentum. So, they will be having the different forms. So, when you substitute, so what happens? So, you suppose you take the x momentum, so it becomes dou u by dou t. Now, that will be, so you had the first term, that is minus of dou p by dou x. So, that was as usual. Now, we have the dou by dou x of tau x x. So, it will be dou by dou x of tau x x, we know it will be 2 mu dou u by dou x plus lambda dive u. So, this will be the first term. Similarly, you will have dou by dou y of tau x y. So, that will be mu of dou u by dou y plus dou v by dou x, and similarly the third term will be dou by dou z of dou u by so it will be mu times dou u by dou z plus dou w by dou x. So, this will be these are the three terms, and then you had the source term, that was Sm x. So, this was the momentum equation, and this is what you get for the x momentum equation. Similarly, for the y momentum equation you get rho of dv upon dt. So, that will be minus of dou p upon dou y, and then you have the terms will be coming like that. So, you will have dou by dou x of, now you have the terms like mu of dou u by dou y plus dou v by dou x. Similarly, in this term you will have dou by dou y of this term will come 2 mu dou v by dou y plus lambda dive u. So, that term will be there in the y term, y component, and then you have the this third term will be dou by dou z of mu times dou v by dou z plus dou w by dou y. So, then and then you will have the source term, that is Smy. So, this is the equation for the y momentum, and when you substitute in the z momentum equation, you will have the equation rho of dw by dt. So, this will be equal to minus of dou p by dou z plus dou by dou x of mu times dou u by dou z plus dou w by dou x. Similarly, dou by dou y of mu times dou v by dou z plus dou w by dou y, and then you will have the dou by dou z times you will have 2 mu dou w by dou z plus lambda div u, and then you will have the source term in the for the z component. So, this is the these are the three equations which are the Navier-Stokes equations, because you have expressed these viscous stresses term in the form of strain rate terms. Now, what we see, if you look at these terms, so if you take any of these values, so we can express them. If you take these many terms, if you take these terms, so you can express that as dou by dou x of dou u by dou x plus dou by dou y, so that will be mu times dou u by dou x plus dou by dou y of mu times dou u by dou y plus dou by dou z of mu times dou u by dou z. So, that will be one term, and there will be another term that will be separate and plus SMX. So, that we are basically writing as the source term. So, if you take this part and we write further, so we are writing basically dou by dou x of 2 times 2 mu dou u by dou x plus lambda div u. So, that is lambda div u, and then you had the term dou by dou y of mu times dou u by dou y plus dou v by dou x, and then you have dou by dou z of mu times dou u by dou z plus dou w by dou x. So, if you try to write further this equation, that you can write as, first you take one of these term together. So, it will be dou by dou x of mu dou u by dou x, then you will have dou by dou y of mu dou u by dou y plus dou by dou z of mu dou u by dou z. So, that is what that is nothing but div of mu grad u. So, that is this is that term. Apart from that, now you are left with other terminologies. So, this becomes equal to this. Now, you have other terms like dou by dou x of mu dou u by dou x, then you have the dou by dou y of mu dou v by dou x, similarly you have dou y dou z of mu dou w by dou x, and you are left with term dou by dou x of lambda div u. So, so now this term can be written as, you can write so this term will be div of mu grad u. So, that will be this term, and then a rest term you can take in the bracket as SMX. So, that way you have taken these bracketed terms. So, this basically this bracketed term is taken into this bracket. So, that is the equation for the Navier-Stokes equation in the x direction. Similarly, so then in that case you can write, so you are writing, so that will be rho of du. So, this is basically rho of du by dt. So, that will be basically div of, so you will have term left is dou p by dou x, it was in the earlier one. So, this is minus dou p by dx was left. So, that terms comes here, and then you have div of mu grad t, mu grad u, and then you have SMX. So, this is the Navier-Stokes equation for the axic momentum component. So, so you will have 3 equations for the x, y and z momentum. So, as that is for the x momentum, and if you go for the y one, it will be rho of dv upon dt. So, that will be minus of dou p by dou y, and then plus div of mu grad u. So, that will be mu grad v, and then you will have S m y. So, this is u and this is v, and the third term will be for the z components rho of dw by dou dt, that will be minus of dou p by dou z plus div of mu grad w and plus S m z. So, you have S m y, S m x and S m z. These 3 equations, they are the Navier-Stokes equations, and normally they are used for while solving, and typically when we use them for the using the finite volume method. Now, if you go for the energy equation also. So, in the last class we had discussed about the energy equations, and for the energy equation which we derived, we had that time E will be for the internal energy component I, plus you have the kinetic energy, that is half of u square plus v square plus w square. So, accordingly you will have the the terminologies coming for that, because the half of u square plus v square plus w square, that part, for that you will have the u square term, and otherwise you have the for the I term coming up. So, you can use this I mean you can write the energy equation also. So, for that, for the internal energy rho of di by dt, so that will also come as minus of rho div u and plus div of k grad t, and then you have the phi plus Si. So, phi is basically you are getting this by the this is known as the dissipation function. So, this phi, which is dissipation function, it is basically mu times 2 times dou u by dou x square plus dou v by dou y square plus dou w by dou z square, and then you are putting into the bracket, and then you have dou u by dou y plus dou v by dou x square plus dou u by dou z plus dou w by dou x its square, and further you have dou v by dou z plus dou w by dou y square. So, this is basically these are the terms that will come under full bracket plus lambda div u, that is square. So, that was basically that you can get when we are we are converting this E term into the 2 terms I plus the other term, that is for the half of u square plus v square plus w square. So, actually that this might be not clear to you, maybe that you can understand what we did in our while we got for expression for the rho of dE by dt. So, that was that was minus of div rho u, and then you had the terms like dou by dou x of u tau xx, then you have dou by dou y of u tau yx, then dou by dou z of u tau zx. So, that way you got all these for terminologies like dou by dou y of v tau so it was xy. then dou by that was dou x, then you have dou by dou y of v tau y, and similarly dou by dou y of v tau zy, and then you have dou by dou x of that time now for the z component. So, w tau, that was x z. So, then you have then you have dou by dou y of w. So, that w will come further tau yz, and dou by dou z of w tau zz. So, this way you had the dou by rho d by dt, and then you had the term div of k grad t, and you had the term Se. So, this was the energy equation which we derived. Now, in that basically what we take E, this E will be internal energy I term, then, and so that will be for the temperature, and then you have the kinetic energy term, that is half of u square plus v square plus w square. So, what we do is normally when we are separating, so you will have the terms for the kinetic energy, and for that what we see that in that case you have the multiplied terms of u times those terms. So, those terms will be with these half of u square plus v square plus w square. So, if you segregate, it will be for the one will be rho times d by dt of half of u square plus v square plus w square, and one will be rho of di by dt. Now, if you see in this term, so one will be for I, which will be for the internal energy, and that will be for, so that we can take for the temperature term, and so that though these terms will go with that term, but for this for this part for of the half of u square plus v square plus w part, that is kinetic energy part, that will be obtained by multiplying the u component with the x momentum. So, that can be understood that this will be basically u times dou by dou x of tau xx, similarly u times dou by dou y of tau yx. So, all these terminologies will be coming for this expression, and others will come with this. So, in that and this will also be divided in two terms. So, it will be minus of u grad p, and accordingly and then you will have the terms like so this is basically pu, and you have u times dou tau xx by dou x plus dou tau yx by dou y plus dou tau zx by dou z. So, this will be further you will have v times the things will come here, v times dou tau xy by dou x plus v times dou tau yy by dou y, and then similarly v times dou tau zy by dou y. So, similarly plus w times you will have these components, basically they will be coming together. So, all these terms will come here, and then you have the u times the source term. So, these terms like you have if you take v times, so v times will be dou tau xy by dou x plus you have dou tau yy by dou y plus dou tau xz by xx. So, that is that will be zy, dou tau zy by dou y. So, similarly for w also these terms will come, and if you take, so that those components will be for the for that component for the d of by dt of half of u square plus v square plus w square kinetic energy part, and for the internal energy part you will have other terms coming, and for that you will have minus of rho div u plus div of k grad T. This term will come with the internal energy part, and then you will have the tau xx times dou u by dou x. Then you have tau yx times dou u by dou y. So, this way you will have all these terms multiplied by these stress term multiplied by these dou u by dou y, and so that way these terminologies will come alongside here, and then you will have surf SI. So, this way you will have, so that is why we have written the expression for dou di by dt, and you have rho div u div k grad T. So, that for that just understanding for the you have here for the div of k grad T, and this term was here. So, if you put that in this term, you will be getting this term, and this phi was will be coming like this. So, this is about the Navier-Stokes equation, which will be solved. Normally we solve with the proper boundary conditions, and then you have solution methodology which is adopted, and then we get the proper value of output parameters that we will see in our coming lectures. Thank you very much.